Alrighty, here we are for worksheet 5, friction, taking a look at problem 8, the last problem on the homework set. It says, a 600 kilogram stone block is being dragged by ancient Egyptians along a stone causeway to build a pyramid. The Egyptians pull on a rope that makes an angle 25 degrees below horizontal. For stone on stone, the coefficient of static friction is 0.5 and the coefficient of kinetic friction is 0.4. Solve for this force, Fp, that pulling force that they need to just barely get the block to slip. And then in part B, we'll solve for how big the friction force is keeping it from slipping if they only pull with 2,000 newtons of force when they're trying to get it moving. Okay, so first part A, how hard would they have to pull to get it to just barely break free and slip? So I'm going to go ahead and do a force diagram for this block. Let's see, can I do it like this? Maybe. Here we go. Yeah, that'll work. So let's see here. We'll go ahead and sketch that. This is problem 8. Okay, so free body diagram. There's that big stone block. And we'll start off by saying, okay, what about ranged forces? There's a gravitational force, mg, and then contact forces. So you say, okay, what's touching the block? And you'll have two things. There's this rope, and then there's the causeway here, right? And so you say, okay, let's start with the causeway. Are those two surfaces being pressed together? And you say, yeah, gravitational force is going to pull it down. These guys are also yanking down and shoving it into the ground harder. So definitely they're pressed together, and that means you'll be compressing these surfaces. They will push back up with a normal force. So this is my normal force on that block by the causeway. Next, once you've got a normal force, you ask, okay, those surfaces, they're pressed together. Are they trying to slide past each other? And you say, sure, these people are tugging it to the right, trying to get it to slip. So there'll be a friction force opposing the slide. And this is going to be a static friction, right? Trying to keep it from slipping. And then the only other thing touching is the rope. So there's that tension here. Now, in the problem, they called that force Fp. They gave it a name, so we're going to use their name for it. Okay, so that's tugging like this, calling that Fp, that pulling force. And we know this angle here is 25 degrees with horizontal. There we go. All right, so that's the setup. We should choose coordinate axes. First axis goes along the way it's moving or trying to move. We are trying to slide it horizontally here. So I'm going to do my coordinate axes. First one goes along the way it's trying to move, and then perpendicular to that. This will be my x and my y axis. We'll call positive that way. Now, what we want to do is figure out how big Fp has to be to get this to just barely break free and start to slide. So let's go to the most important formula in physics, sigma F equals ma. We're trying to solve for a force. Let's go ahead and do F equals ma to find that force. I could do this equation twice, once for the horizontal axis, once for the vertical axis. I can go ahead and get this out of the way now. All right. So if I do that, horizontal axis, and we'll do it for the vertical axis too. Okay, in the horizontal axis, you say, well, actually, wait. If there's a force that's not going along one of those axes, it has to get replaced by components that are going along the axes. So I'm going to have to split Fp up into a horizontal or x component and a vertical or y component. Right angles between the components, making a chain of arrows from the start to the end of that force arrow. So this and then this. This side is adjacent to the 25. Fp is the hypotenuse, so we're going to use the cosine function. This is the hypotenuse times the cosine function. And this will be that hypotenuse times the sine of that angle, 25. All right, that's all my forces. Let's go to F equals ma. Horizontal axis, we'll be doing right minus left. So that'll be that Fp cosine 25 going right minus the static friction going left. All right. And then you say, okay, now what's going on here? You say, we want this thing to be at the very edge where it's about to break free and slip. Okay, and that tells us two things. One, we are not accelerating yet. We're on the edge of about to accelerate. So I'm going to say the acceleration is 0. Right, so that whole right side will be 0 because we are just about to slip. And because we're just about to slip, that static friction is at its maximum. It's just barely able to keep it from slipping. So this is the max value of static friction. Now, if it's the maximum, then we know we're allowed to substitute in mu Sn for the static friction when it's at its max. That's when it's equal to the maximum value. Before that, it'd be below. This is when we've built all the way up to that maximum amount about to break loose. So I can substitute in mu Sn where it says static friction. All right. All right. So at this point, you're saying this is looking good. FP is what I'm trying to find. Mu S, they did tell me. I know that it's 0.5 is my static friction for stone on stone. But I don't know that normal force. If I knew that normal force, I'd be able to solve for FP. Well, a normal force is a force in the vertical axis, so let's go to the vertical axis. I labeled this wrong. This is XX. This ought to say YY. Sorry about that. This is the vertical axis over here. I don't know what I was thinking. Alrighty, so up and down force, we do forces up minus down. So you'll say forces up, that's just that normal force that we need to find to help us out here. Forces down, so it's going to be minus mg. But then also don't forget, these folks are pulling down at an angle. Maybe like, you know, it's a great big huge stone block and a bunch of people yanking that are shorter than it. So they're pulling down at an angle. So they're going to be shoving it actually into the surface harder here by that FP sine 25. Now, is this block accelerating up and down? No, we're dragging it along a level surface. And so the acceleration up and down is 0. Okay, so there we go. Now this equation, normal force, I don't know. FP, I don't know. FP is what I'm trying to solve for. So I got two unknowns, N and FP. In this equation, I got two unknowns, N and FP. I'm just going to substitute and solve. I want to solve for FP, so I'm going to get rid of N. So I'm going to get N by itself and then substitute in where it says N there. So rearranging, this N is going to be equal to, I'm going to add mg to the other side, and I'm going to add FP sine 25 to the other side. Okay, now I can take this whole mess here and substitute it over here where I see N, right, to get rid of N. So I'll just have an equation with FP as my unknown. And then where it said N, I'm going to be putting in mg plus FP sine 25. Okay. And then that's going to add up to 0. There we go. Okay. So looking at this, the only thing in this line that I don't know the value of is FP, which is what I'm trying to solve for. So life is good. Okay, I'm going to distribute this mu s to both terms, this minus mu s to both terms. That'll give me two terms that have FP in them and then one term that doesn't. The term that doesn't, I'm going to move to the other side. So I'm going to do two algebra steps at once. I hope you don't mind. Remove this minus mu s times mg, so I'm going to add mu s mg to both sides. So that'll move to the other side. Now a minus mu s times FP sine 25. That's going to be a minus mu s times FP sine 25. And on the other side, I'm going to have that mu s times mg. Now positive because it got added to both sides. Okay, again, now I have just all my FP terms on one side, all my terms that don't have FP on the other. I'm going to go ahead and get that FP by itself by factoring it out. So I think I'm going to stop my color coding now, if you don't mind. So I'm going to have FP times the quantity cosine 25 minus mu s sine 25 equals mu s mg. Now this bit that I'm multiplying the FP by, I'm just going to divide both sides by that bit in parentheses. So finally, I'll have my variable isolated by itself like I wanted, mu s mg on top, and this bit in parentheses, cosine 25 minus mu s sine 25 on the bottom. I can put my values in now. Mu s I know is 0.5. The mass, I was told this block has a mass of 600 kilograms. Okay, and G is 9.8. On the bottom, I've got cosine 25 minus, and that mu is 0.5 times the sine of 25. There we go. I'll punch that in my calculator. Let's see, 0.5 times 600 times 9.8 divided by the quantity cosine 25 minus 0.5 times sine 25. And I get that the force they need to get that block to slip is going to be 4,230 newtons. All right, so that's how hard they have to pull to get that block to slip. Okay, so that's part A. All right, now we're going to go to part B. Part B, they say, hey, how big is that friction force going to be, keeping it from slipping, if they pull with 2,000 newtons of force? Okay, so if FP is only 2,000, now it takes 4,230 to get it to slip. We're only going to pull 2,000. Well, this static friction then isn't going to be at its max. So I can't just plug in mu s n to figure out how big it is. How big is this static friction going to have to be? Well, my force diagram is going to look the same. And that means my first lines here are going to look the same. Same forces. Okay, are we accelerating? No, we're not pulling hard enough to make it slip. So that's still 0. But this is not at the max value anymore. Okay, but these two lines otherwise, other than the fact that this will not say max, it's not at its max. And this is, and you say, and in fact, this is what we're trying to solve for this time, is that Fs. You say, otherwise these lines will look the same. So I can still rearrange this one to get n is mg plus fp sine 25. That work will look the same. All right, if I wanted to, but I'm not even going to need that because I'm not going to split this up into mu and n. I just want to know how big Fs is. So I really just am going to use this expression for part B. Okay, part B, we're not pulling hard enough to make it slip. So the force diagram, this is part B, sorry, I'm going to squeeze it in here. Force diagram looks the same. So Newton's second law, the sigma F equations, look the same, except static friction is not at maximum. So what I'm going to do is I'm going to go ahead and I'm going to move. I'm just going to copy this one down. I'm going to have this component of the force pulling right and that static friction pulling left. balancing it out because we're not accelerating yet. So you can see those two forces are going to add to 0. So I'm just going right to FP. I'm trying to save some space because I'm running out of paper here. Minus Fs equals 0. So I can see that Fp cosine 25 equals Fs, which is what I'm trying to find. I just plug my value in. Fp, they say, was 2,000 newtons times the cosine of 25. That's how big the static friction is. I can just plug that in my calculator. 2,000 times cosine of 25. My calculator tells me, hey, that static friction that's fighting that 2,000 newtons only has to be 1,812 newtons. Okay, actually it rounds up to 1,830 newtons is that static friction. Okay, because the full 2,000 isn't trying to make it slip. Just this component is trying to make it slide. We're just balancing out that component. Okay, and that is problem 8.